Alrighty, folks. Today we're going to talk about atoms and a whole bunch of stuff, vocabulary words basically, that are affiliated with atoms. And whenever I start this PowerPoint, you guys all get nervous because you're like, oh my God, I hate chemistry. Please don't worry. You're not going to be balancing equations. You're not going to be asked to do any math. All right? No. It's just that this stuff is going to come up. We're going to be talking about minerals. We're going to be talking about elements. And in doing so, they can't help but use some of these words. You've had it before. You had it, whether or not you had chemistry in high school, certainly when you had a sort of a physical science class, you came across some of these words. So they're not totally, completely new to you. We're really refreshing your memory, okay? And if you didn't do so swell on it the first time, well, now's a chance to do a little better. So without further ado, atomic review. And I do not mean for that to rhyme. So what is an atom? An atom is the smallest piece of an element that still retains the properties of that element. And you could use the word particle here if you wanted to. Pieces part. A lot of times when we talk about stuff like this, I use a Lego analogy, right? And, depending on the conversation, I reuse some of the parts. But let's talk about that one little thin, one square Lego. All right? The tiniest little one that you hurt your fingernail trying to pull it off of the other pieces. That one. All right? Those are your atoms. And you make all your other Legos. What is it? 3 or 4 of those makes the regular height Lego. All right, and then you could add, if they just gave you a kit full of those in theory, you can make every other Lego size out of those. That's kind of how atoms are. And it's still a Lego, right, arguably. It still has that little round nub on top, the little hole in the bottom. It's still made out of plastic. Maybe it has the word Lego imprinted on it. So you still recognize it as a piece of Lego, however annoying it happens to be. So those are your atoms, they're the pieces parts. And as you heard in the video the other day, hopefully you watched the video, we've been theorizing that there's something out there for as long as we've been thinking, probably. All right? Some substance that everything is made up of. I want to say it's Plato. I could be off on that one. He was the first one to write it down and get it published. But I'm sure that he got that idea from somewhere as well. You have to apologize as we tap through some of these to get them highlighted. This is, again, from way, way back. And I know how to turn off that click as you highlight thing. For some reason, it won't work on this PowerPoint. And I'm just too stubborn to retype the whole thing. So we just click through 6 times sometimes. Now, traditionally, I ask you guys, what are the parts of an atom? Over the years, when I actually got the PowerPoints posted on time, that kind of became a moot point because you guys, at least half of you, would have the answers right in front of you. So I kind of got out of the habit of asking. Now this semester, I haven't been a good teacher and I haven't put up the PowerPoints yet. Sorry about that. I meant to do that over the weekend. But you guys probably would have guessed these 3 things, right? So instead, we're going to play a bit of a guessing game when we want to talk about the properties, for lack of a better word, of these 3 things. You guys need to know 3 things each about these 3 things. All right, and they're similar. It's not like 3 different categories for each one. They're all the same. You're going to want to know where they live in the atom, where they are in the atom, what their charge is, and what their mass is. All right, where they are in the atom, what their charge is, and what their mass is. let's talk about charge first. Proton. Anybody? Everybody? Positive. Good. Proton, positive. Excellent. Neutron. Yeah, we stammer on that one because we know it like it's N and P, and it's not neutron negative. That's for the other guy. It is neutral. Neutron neutral, all right? It's got that new thing shared between both of them. So proton positive, neutron neutral, which means essentially zero for a charge. And then electron is the negative. That one doesn't have any matching letters or anything like that. So positive, zero, and negative. Excellent. Oh, what's the next easiest thing? Next easiest thing, where do they live in the atom? How about the proton and neutron? They both live one place in particular. Anyone remember that vocabulary word? Nucleus. Excellent. All right. And I'm not going to get you on spelling whether you use EAS or EUS. It's your call. One of them's right, one of them isn't. But nucleus. I'll be happy if you remember the word. And what is the nucleus? Anybody, everybody. Not just where the proton and the neutron live. Where's it at in the atom itself? It's in the center. So the nucleus is the center of the atom where the protons and neutrons are located. This isn't a verbatim kind of definition to remember. It's just, FYI kind of stuff if you don't remember it. This is also, as you'll see in a moment, where the majority of the atom's mass is located, in case you cared. So, neutron is the center part. It's in the middle. It's where everything's happening. Excellent. And it can contain any number of protons and neutrons, right? You guys remember what you remember about that. So where are the electrons at then? The cloud. Excellent. Anybody, did you have chemistry? Miss Pham, right? In high school. Okay. And they talked about the cloud? Okay. They talk about rings anymore? A little bit? Okay. Some not. I got a couple head shakes and I got a no. Maybe that was, I had it in high school. I don't remember high school chem. I remember I caught my lab book on fire in high school chem. Crucibles get really hot. I took a crucible set on my lab book that had been on the Bunsen burner, and it literally ignited the paper. It was pretty cool. I didn't know that could happen. But college chem, 1s2, 2s2, 2p6. Well, oh my God, I hated that. That's the rings I'm talking about. And the reason, I think that's the Bohr model. That could be. The reason they use that, of course, is because you need to balance those stupid equations, right? And I appreciate chemistry now. I badmouth it a lot, and I love our chemists here. It's a great class, and chemistry's super duper important. But it was a pain in my butt, basically because I didn't give it the time it needed. So if you guys have chemistry in college, plan on giving it a lot of time. Okay, it needs it. So, anywho, we had to balance those equations, and really the only way those equations could balance for your freshman chemistry mind was that if they taught you this shell thing, and you got to swap your electrons over, and they share here in this case, and then remember valence and all those words. But then you get a little farther along in chemistry, and they tell you, well, yeah, that's just a snapshot at any given instant that may or may not actually exist. And really, we're not even sure if electrons exist. They're there, probably. Electrons are crazy. Crazy things. It could be like here 1 second and in Neptune in another second, and then in your cat in the next second, and then in your coffee mug. They're learning. Every day they learn more crazy crap about electrons. And they're in a fuzzy little cloud. That's the best we could really say. Is the electron cloud. And when I say it that way, you're like, oh, yeah, electron cloud. I've heard of that. But in order to get you through freshman chem, you got to learn to balance those equations. And a fuzzy little cloud doesn't really lend itself to balancing equations very well. But that's the reality. Okay. So, yeah, we're going to go with that. electrons are outside of the nucleus in a cloud. If you remember rings, again, I'm not going to yell at you for saying something about rings when I ask you something. But the point is that they're outside of the nucleus. All right. What we've got left is mass. All right. Anyone remember what a proton weighs, or a neutron for that matter? That's pushing the limits of the memory, huh? All right. What we say is 1 AMU. And I'll tell you what AMU means in a minute or two. 1 AMU. A proton has a mass of 1 AMU. A neutron has a mass of 1 AMU. And did I actually accidentally say the word weigh a couple minutes ago? You guys should know from your first lab homework, what's the difference between weight and mass? Is there a difference? Or are they the same thing? They are different. We should not use them interchangeably, but we often do. All right, so they have a mass of 1 AMU. AMU just means atomic mass unit, and it is a really small number. You'll see it on a slide here in a couple minutes. I do not need you to memorize it, okay? 0 point in that. But suffice it to say, as you might hope, suspect, it's a rather small number. So we told you that the majority of the atom's mass is located in the nucleus. That's why, okay? Because electrons, bless their little hearts, as important as they are, they're practically massless. We can't say they have no mass. We can't say they have 0 mass. What they say is no significant mass is kind of the verbiage they use. You could have a whole herd of them outside or 3 of them outside, and it won't change, as far as you're concerned, it won't change the mass of the atom. It gets into some sort of circular logic, again, referencing your first lab homework of matter and mass, right? The definitions, remember those? Matter is anything that takes up space and has mass. Mass is a measure of your matter. So you can't say that it's massless, because then you're saying it isn't matter, and it has to be matter because it's a piece of matter. So we can't say massless. But all right, so you got 3 things about each of those 3 things, right? Positive, neutral, negative, nucleus, fuzzy cloud, 1, 1, and yeah. Excellent. So you're going to see that in slides coming up through here. We're going to jump through it because you guys have all been taking awesome notes for the last 5 minutes, writing down what we were talking about instead of just waiting for these silly little slides to come through. So we got protons, as it says, subatomic particle that contributes mass of 1 AMU. It contributes a single positive electrical charge in that atom, and it's located in the nucleus, right? Everything I just told you, everything we just talked about. Same thing for the neutron. And again, if you didn't write anything down, don't worry. Send me an email, and it'll jar my memory to post these for you guys. Subatomic particle that contributes mass 1 AMU, contributes no charge to an atom, located in the nucleus. And electron. The only thing that's really new on here is I keep every slide opening with subatomic. And you probably heard the word before. But we didn't define it. All right, sub means, well, below, right? Substandard, subpar, submarine, substantial. That one might not work. But so subatomic just means below the level of an atom, right? So that's what subatomic means. But otherwise, exactly what we promised. Oops. So here's that AMU. AMU, again, stands for atomic mass unit. All right, and I told you it was a teeny tiny number. -27. So already when you see, hopefully, again, you remember this stuff. This is why we gave you those review labs and why we had you watch that Cosmic Voyage video. You see these negative numbers, you know you're going into decimal land, right? 27 times. So you take that little pencil, and I still do this. Don't be ashamed to trace with your pencil when you're counting, all right, how many negatives you're over. I don't know if they taught you that. Hopefully they taught you that back in school. I still have to do it with my pencil just to keep my places straight. So 1.66 times 10 to the negative 27 kilograms. It's science. They love metric. Okay. And it wouldn't be honest, if that were in pounds or ounces, it still would be a meaningless number to you, right? Because it's so small. But again, this super, super, super tiny mass we would expect because we're talking about not just an atom at this point, but parts of an atom. So if we were to go back to that Lego metaphor or analogy, I don't know which one it is, and now we're talking about that single Lego that's, we'll say it's 3 high. I'll have to go home and check my kids' Legos. You guys remember how many singles does it take to make a full height Lego? Is it 3 or 4? It hasn't been that long since you guys played with Legos. I think it's 3 as well. Thank you. All right. So now you got 3 little jobbies in there making 1 square. Okay. And you pull off one, there's your proton. You pull off another one, there's your neutron. And in this case, we just have 1 electron in there. But so now we're using that Lego analogy one more time, taking that atom apart. All right. And seeing the pieces, parts inside. So an AMU, an atomic mass unit. Nucleus, we talked about this as well. Central portion of an atom, 99% of the mass. I didn't tell you that before, I just said most. And this is where the protons and neutrons live. I anthropomorphalize a lot, I apologize. Again, that's part of, we talked on the first day about agendas and when someone's telling you and giving you information. My job, my opinion, is to have you leave this room thinking that science isn't scary, or at least as scary as you thought it was. So doing things like saying where it lives and stuff like that, that's just sort of softening the edges a little bit, hopefully. So, because I could be very formal, but we'll leave that for the actual chemists. So we talked about this as well, subatomic. Yeah, I suppose some world they might hyphenate it, but subatomic. We go to any questions about protons, neutrons, electrons, because we're really just getting started here. Okay. And I will not reuse the Lego metaphors, I promise, at least for a while. Because now we're going down sub-atomic. Elementary particles. And I've been saying this for years, ever since I added this slide. I don't know why we call them elementary instead of elementary, but whenever they say it, they say elementary. It's not like you went to elementary school, right? You went to elementary school. Same word. Basic is what it means. Foundational. Basic building blocks of the universe are these elementary particles. They're the pieces, parts that everything we've just been talking about are made of. And we've got 2 basic kinds that I'd like you guys to familiarize yourself with. One are called quarks. Again, you may have heard of them. And the other are leptons. You probably haven't heard of those. So quarks and leptons. And I skipped over the official definition for an elementary particle. A particle not known to have any substructure. In other words, as far as we know right now, clincher, right there, of course, As far as we know right now, there ain't nothing smaller. We've known about quarks since the mid-60s, I think. Early 70s, if that. And so what is that, 40, 20, good 60 years. And they haven't found anything smaller yet. If you pay any attention to this stuff whatsoever, they're looking. That's what these particle accelerators are all about. Large Hadron Collider, CERN. You heard of CERN? It was in the news a while back. Everyone was really concerned when they booted up CERN. I think it's in Vienna or Switzerland over there somewhere. Because the scientists got cocky and they said they were looking for the God particle. And I think we talked briefly the other day about mixing God and science, and that was their huge mistake right there. That isn't what they meant at all, of course. What they meant is like the foundational, truly foundational beginnings. And so that got everybody all in a tizzy, and they were worried that they were going to open up some sort of black hole or wormhole, and rainbows and unicorns would come out of it, and it was chaotic. The funny thing is, as soon as they booted it up, it went and then died, which was kind of great. But they fixed it, and then they got off to a good start. But everyone was freaking out. We've had one under Chicago for, 50 years, 60 years. Fermi Labs in Chicago, all right? We've had a particle accelerator right here in America. Nobody ever gave a crap about it because they were smart scientists and didn't blab about it. Thing with CERN is bigger and is, I'm not sure, I don't follow racing a whole lot, horse or cars, but I'm guessing the bigger the racetrack, the faster you can go on it, right? Presumably. And so that's the idea with CERN, is it's so much bigger. They could get these things zipping around so much faster. And just like car racing, they want to watch for the crashes. That's what they're trying to get at these things, almost approaching the speed of light and smashing into one another and seeing what it makes. So, anywho, so that's we're still learning this stuff. My point is, and this not known to have substructure. By the time you have kids, maybe there'll be pieces, parts to quarks. Who knows? That's the beauty of science, though. So what the hell is a quark? Not a misspelled quack. It is its own thing. Elementary particles that combine to form composite structures. Ugh. All right. Hadrons. So remember the word lepton a second ago. If you want to, I don't have you remember the word hadron, but if it, in other words, you won't see it on a test. But if it helps you to keep it straight, protons and neutrons are hadrons. And electrons are leptons. So technically speaking, everything's either hadrons or leptons. But I kind of felt you didn't need yet another vocabulary word thrown in right now. So what we tell you are that quarks go together to make protons and neutrons. We don't need to make electrons because they're already elementary. You saw that on the previous slide. I might not have pointed it out, but that was the lepton. Those are already basic, primal, day one kind of stuff. In the beginning, there were quarks and electrons, as far as we know. If you're ever bored and you want to find some silliness in science, read about quarks. They have different spins, which is how they identify them, and they call them flavors or colors. I forget. It's been a while since I've visited the Wikipedia article about this and whatnot. But when you're getting down into this subatomic physics, it's pretty wonky stuff. And these are crazy physicists as well. Really interesting to talk about. I actually ran into, we still call it Carousel Mall. I know it's not Carousel Mall anymore, but you guys know what I'm talking about, in Syracuse. And I think it was when my daughter was young. No, it had to be my son because they still had a Barnes & Noble there. So I was on the carousel for like 3 or 4 times, and so was the guy next to me. So eventually we started talking. He was there because his wife was doing a book signing at the bookstore. be it a Borders or Barnes & Nobles, whatever the heck it was. Turns out he was and the word keeps jumping out of my, quantum physicist. There's the word, quantum mechanics, and quantum. They talk about quantum when they talk about this stuff. He was a quantum mechanics guy, and I was having him explain something to me, and it was so surreal. As the carousel is going around and the music's swirling around, and he's talking about all this stuff, and it was interesting conversation. Interesting conversation, to say the least. Flavors. Pretty sure quarks come in flavors. And I know they've never licked them because they haven't even seen one. Leptons. Leptons do not combine to form composite structures. And your example of a lepton is an electron. And neutrinos, which we don't really talk about. Any chemistry majors in here? Okay. There's one sort of issue with this, and if you know a whole lot about chemistry, the issue comes up. I won't bring it up because I don't want to confuse you guys, and it still confuses me. But there is some groups of people who talk about protons and neutrons as simply taking and removing electrons from them. And if that is a true way of thinking about protons and neutrons, then this definition is false. But I guess I did tell you about it, sorry. But at any rate, so this is the textbook definition. But that's a pretty neat idea that you could change a neutron into a proton or vice versa simply by pulling a charge out of it. What you guys know and love is the atom. All right. Came from Ernst Rutherford, and I was teaching in 2011, and I said, and I was teaching before 2011. I said, boy, we haven't even had the structure of an atom for 100 years now. And then I would say, hey, it's the 100th anniversary, and now I could say we've known more or less what an atom looks like for over 100 years. Point is, that's relatively new in science. That's getting to the old point. And by that we mean the nucleus separated from the electrons. Okay? Yeah. Probably context. I don't think I asked you what year or what person. Good question. This is a more, I consider a sort of a 1950s nuclear age version of it. And, this actually leaves the cloud behind and gives us that image of the shell, the electron shells. But this is very much a Cold War era kind of, you got your nucleus in the center and those electrons zipping around it. Reminds us maybe of our solar system even a little bit. But again, this is just yet another way we model that. If I had a matching diagram, at least I don't for this, but if I did, you could very easily tell me where the protons and neutrons lived, what that little circle was called, and who was zipping around in those rings around it. But you basically see the 9 questions, and a whole lot of you weren't taking notes, and that's fine, because again, you didn't have this stuff too long ago in your careers. But it is, I think, 9 points right off the first test there, okay? The positive, neutral, negative, nucleus, outside the nucleus. Those 3 things about the 3 things. So if you know this stuff already, do yourself a favor and brush up at least a little bit before the test, because if that's an easy 9 points for you, then that's awesome. We want you to have an easy 9 points. Question or just stretching? All right, so we didn't get too deep into it, but any questions about quarks, elementary particles? Just wanted to introduce the idea out there. That really only becomes relevant in the semesters when I do cosmology, when we take the creation of the Earth all the way back to not just the creation of the solar system, but the creation of the universe, which I sometimes do, depending on the semester. So you won't hear much more about quarks unless we do that. So now we're taking everything we built and we're talked about and we're building and moving forward, okay, to the next word, elements. You guys are familiar, hopefully, with the periodic table. Again, nothing you need to memorize, but in theory, you might look at one when we're doing the minerals chapter, and we want you to have some familiarity with it. What did we tell you that an atom was? Remember the definition of an atom without me clicking all the way back through there? Who wrote it down? So the smallest part of an element that retains the properties of that element. Thank you. So we're there now. We're at elements. And these are, I hate to keep using the word, these are your basic fundamental structures right here. At a certain level, these are your basic fundamental structures. Because who goes below the elemental level in everyday conversation? Well, only a handful of folks, right? Certainly in the lab, you're going to be rattling off, elemental compositions. You're not going to be fussing with the protons and neutrons. So, everything is relative, right? And that's sort of the point of it. These can also be viewed as fundamental building blocks. It's what the universe is made out of. Even though we just spent 20 minutes talking about the stuff that makes these guys, all right? So, keep it in perspective. Depending on what you're talking about, they can all be fundamental building blocks. This definition is horribly flawed, and we will talk about it. When I first started teaching this class, we had Chem 090, which was just intro to chem. Probably, well, it was even, I won't say lower than what you had in high school, but there was no lab to it, all right? And I don't even know what degree used it, but some degree used it. So, basically like physical science. I had one of their books, and I opened up the glossary in the back because I wanted a really simple, fundamental definition of an element. And I found this one. And I checked around a couple other books, and they were all fairly similar. Now, I know this is unique to the field of study that we're in, geology or science. But how many of you have ever heard of radioactive decay? Radiometric dating, right? Pretty much all of you. Even if you didn't raise your hand, I know you have. Everybody's heard of it, all right? And what's the point of that? What decays into what? Give me one classic example. Oh, you might not remember that, but anybody? Come on, rubidium, strontium, everyone? No. Uranium to lead. A lot of people know uranium to lead, okay? But there are others. There's a couple different decay series that we look at. But if you know it, you know uranium to lead. And what's that say? That's telling us that uranium, over time, the word's half-lives, right, turns into another substance called lead. What does that definition say? An element is something that can't be turned into something else. So, yeah. Again, good enough for freshman chem, but when you enter the realm of geology, it's kind of like that ring structure with the atoms, okay? It works for one conversation, it doesn't work for another conversation. You get a little further along, they say, oh, yeah, what we told you your freshman year. That's just what we tell you so you can understand the other stuff. So this is one thing about, that's important in geology. We don't talk about that kind of stuff too much in here because traditionally we had another class, Geology 102, that was historical geology. Lots of fun. That's actually my side of geology. And we talk about all the age dating and all that stuff in there. So we don't talk about it too much, but it is, the fundamental basis of when they tell you how old something is. We're looking at elemental decay. So an element. There's 100 and some odd elements on the periodic table. You guys probably could rattle off a dozen or so, most of you, if you're not even, a science geek. If you are, you probably can do a handful more. I used to be able to do about the first dozen in order. I don't think I could anymore. That thing. All right. Again, you've all seen that. Oops. How is this arranged? Is it alphabetical? Order of discovery? Anybody? Yeah. By mass. Okay. All right. So lowest to highest, highest to lowest. What is lowest to highest? Okay. So what you're saying is that presumably the upper left-hand corner, right, is the lowest mass. And then how do you read this? You guys go left to right. You go up and down. Somebody else help her. All right, left to right and down as you go across. So you jump from hydrogen, H, over to the He, helium, lithium, beryllium. I would have got 4 of them right. I always forget about boron there. Hydrogen, helium, lithium, beryllium, and boron. And you go through that a ways. Except for this weirdness down at the bottom, right? What is it, the actinide series and the lanthanide series? Actinium and lanthanium, but I think they conjugate it differently. There's a chemistry reason that they pull those out, and we so don't need to worry about it. But otherwise, they're in number by increasing mass. And where is... Do I have a blow-up of this? Hold on. We're going a little different way today, and that's cool. I don't have a blow-up. Where is that mass number in one of these squares? This is horrible to see. But do you guys remember? Is it the number at the top or the number at the bottom usually? Try to genericize it a little bit. Yeah. Number at the bottom. And it's going to be the bigger number. I'm surprised I don't have like a single one of these squares enlarged. Well, what's the numbers across the top then? That are in order. 1, 2, 3, 4, 5, 6. Yeah, it is. And we've got a vocabulary word for that coming up. So the numbers across the top are the number of protons. And that's, I don't want to say technically how it's built, but it's technically based on number of protons. The mass is very, very much related to that, okay? There's a couple glitches with the mass idea, but it is very much connected to the number of protons. And we're going to Sesame Street through a little bit of chemistry here again. So if you're fond of chemistry, please forgive my Elmo version. All right, so before we get back into that, we want to talk about something else. We just talked about an element, right? A compound. Now what do we got for some wonderful textbook definition here? A substance formed by the chemical combination of 2 or more elements has properties different than those of the individual elements. Yeah, that's, again, pretty straightforward textbook there. A compound is a mixture, right? You know that. Somebody tell me a compound. Big one right off the bat, usually people say. Carbon dioxide. Did I hear sugar over there? Or what did I hear? H2O. Okay. It's like sugar. Geez, that's a big one. C6H12O6. Is that glucose, maybe? I think. It's photo. I only remember that because of photosynthesis. All right. So H2O and what did you say over here? Carbon dioxide, CO. Oh, and I just did the damn thing I was supposed to have you guys do, CO2. So what's in carbon dioxide? Carbon, obviously, and the di means 2. Okay, what if something's mon? What does that mean? 1, okay? So C, and then 2 oxygens. Good. Let's not screw it up for water. All right. Somebody mentioned water. What's in water? H2O. So that means how many? Well, what's H, you guys? Hydrogen. What's the O? Oxygen. Where's the 2 go? Is it 2 hydrogens or 2 oxygens? 2 hydrogens. Good. Good. You guys are golden. So that's how you read those. All right, and that's fine. You all walked in the door knowing that. But I want to instill in you just a little bit about the actual magic that's going on here. They may tell you that you may have heard that chemistry is baking, and baking is chemistry, and it truly is. You throw a handful of ingredients together, and they mix and meld and form and make something new, and brownies are always just amazing when you get them done, okay, as an example. But let me give you a much crazier example. And this, as I said, really highlights what I call magic here in chemistry. The next compound that most people come up with is salt, right? What's salt composed of? Okay, somebody give me one ingredient. No hydrogen. Sodium. And what's the other ingredient? Chlorine, okay? They always say sodium chloride, but the element is chlorine. So sodium, what's the abbreviation for that? Na, good. Na and chlorine is it CH or Cl? Cl, good. So NaCl, all right? No fancy numbers, nothing in it. Sodium is a soft, sort of Play-Doh-y, powdery thing that's flammable in air. Chlorine is a green poisonous gas. Again, at surface level kind of pressures and temperatures, whatnot. You mix a flammable solid and a green poisonous gas together, and they make French fries taste good. That just makes zero sense. The properties are different than the original properties. All right? We wouldn't all have problems with eating too much salt in our diets if it lit us on fire or if it killed us every time we ate it. They lose those properties and they gain something new. Water's another great one. Water's truly amazing. It's one of the few, if not the only substance that exists in all 3 states of matter at the surface of the earth, right, under normal circumstances. But just, again, at base level, hydrogen's a gas, oxygen's a gas. You mix these 2 gases together, you get a gas or, as we said, a liquid or a solid. That's pretty amazing. Hydrogen's incredibly flammable, right? We stopped using that a ways back, although they're toying with it for cars for some reason. Isn't that what the Hindenburg used, hydrogen, I think? I think so. Not a good idea. Oxygen. Well, oxygen, we love oxygen. But again, too much of it could be a bad thing. Too little, definitely a bad thing. So compounds are really special. And I don't, expect you to leave this room thinking all this amazing stuff about compounds every time you see one, you ooh and ah. But do keep that in mind. There's some serious, again, if you're trying to find an appreciation in chemistry, this is a great place to start. To get past all those balancing equations and everything. Compounds truly are wonderful. So there's some sodium up there in the upper right-hand corner. There's some chlorine there. And again, it makes those wonderful. And perfectly cubic little crystals on top of it all. That's just the geology dork coming out. But perfect little cubes. All right? Amazing stuff. Yeah. This is kind of, if anything, just a pluralization rule, just to set you straight. Very few people make this mistake. Every so often you'll hear it, though. When to use atom, when to use molecule, all right? Atom is when you're talking about a single ingredient, a single element. We have an atom of hydrogen, a hydrogen atom. An oxygen atom. A molecule is when you've got multiple ingredients. That's those compounds. And I know I have some big wordy way of separating them, but that's the gist. Okay? Molecules relate to compounds. Atoms refer to elements. Like you would never say you have an atom of water. You have a water molecule. You don't have an atom of air. Let's pretend air is a fixed compound. It varies a good bit, but let's pretend for a moment that air is a fixed compound. You would have an air molecule. And again, that just sounds right. You've always heard it that way because that's one thing teachers have at least been consistent about, and in media, the news, and so on and so forth. We do get these rules correct. But just it's good to have it down on paper. All right. So I don't know why this is so separated from the conversation that I started a couple minutes ago. I probably just jumped the gun. But we're back to talking about the periodic table. Okay? So that number at the top that you guys correctly surmised was the number of protons. And goes 1, 2, 3, 4, 5, 6, all the way across from left to right, all the way down, except for those two removed series. That's your atomic number. All right? The atomic number is the element. The number of protons is the element. The mass, as I said, can vary a little bit. We'll talk about atomic mass in a moment. But the atomic number is just that much more important. Number of protons. So in theory, what we're saying is, I don't even know if this can be read. Surely can't be read on my laptop screen. There's a 6 in the upper corner of carbon here, a 7 in the upper corner of nitrogen, an 8 in oxygen, and so on and so forth. So we're literally saying, if you add another proton to carbon, you're going to make nitrogen. All right? The atomic number defines the element. And that's important because, and here's where the Sesame Street comes in. I'm going to tell you that in a nice, happy element, element. In a nice, happy element, you're going to see the same number of neutrons as you see protons. They like, again in quotes, they like to balance each other out. This is why what we originally said about them being arranged in order of mass is more or less right on, because if you're going to have 3 protons, you're more than likely going to have 3 neutrons. You have 12 protons, you're more than likely going to have 12 neutrons. So your mass increases evenly all the way across. It is all about the number of protons, but it is also true that generally speaking, asterisk, generally speaking, the same is true for the mass. There is an exception to that rule. So we could, and we're going to ignore decimals. Based on what I just told you, if carbon is atomic number of 6, we would expect its mass to be 12. Good. Oxygen is 8, we would expect its mass to be 16. Everybody, I want someone else to answer this one. Sulfur is 16. We would expect its mass to be 32. So you I just need to know that you guys understood that. Okay, not just blinked at me. So you do. It's great. The problem is it doesn't take too horribly long to get into the periodic table where you go and you find 23 for atomic number. And I'm making this up. Don't quote me. 23, and the mass isn't 46. It's 47 or 48 or 45. We have a word for those. Again, a word you've heard. Isotopes. All right? Not on the periodic table, and sometimes they don't even show up on the periodic table. Periodic table gives you the most stable version, is what I've been told, what I understand it to be. So you will see on the periodic table every so often somewhere where the mass is not twice. And that is a variance in what, you guys? Protons or neutrons? If the mass is off from what you would expect, it's because of extra whatses? Neutrons. Because why? Well, if you change the proton, what are you changing? The element. You can't mess with the protons. You add a proton, you change the element. So you're messing with the neutrons. And again, the why, the how, that's all that equation stuff I promised you we wouldn't do. I don't want to do, and maybe one or two of you do, but that's not where we are. That's for chemistry. But if we don't talk about this stuff, inevitably someone will say, wait a minute, you told me that the mass is always twice, and looky here at this one, this, you know. So we talk about it, and it's important too. The other reason isotopes are important is, again, in geology, some of them are actually less stable, which we like, and we watch them break down. So it's not just uranium to lead, it's uranium-238 that they watch. And it goes to lead, I don't know what the hell it is, I forget what number lead it is. But it's certain isotopes of these things that we like to watch and trace. And I think that's probably what I'm getting at here. Oh, no, this is about carbon. So there's carbon-12, which is normal carbon, and then there's carbon-14. You've probably heard of carbon dating. If you watch, like, Nature Channel, you watch anything with, like, Egypt and mummies and stuff like that, they don't use uranium to lead. That's way too big of a gap. They'll use carbon dating. Carbon dating's, well, I don't know where it's at nowadays. It used to be about 10,000 years is a good buffer factor in there. So carbon-14 decays into carbon-12, and they measure ratios of the two. I think it briefly goes to carbon-13. That's why that's there. But so yeah, isotopes are important. But your basic definition here, okay, that's when we see that an element where the atomic mass is not twice the atomic number, as I've trained you to expect. Okay. Questions about isotopes, atomic number, atomic mass. Like I said, it was a little out conversationally of context, but ooh, what's this slide? Why does it say why? Oh, why do this? All right. So you're thinking this is geology class. Why are we talking about this? I'm using this in my earth science class as well, more than likely to say, why did we do this? Well, anywhere from atmospheric studies where they talk about elements in the air, compounds in the air, acid rain, right? That's sulfur dioxide up in the atmosphere. Global warming, you're talking about carbon dioxide and a handful of other guys. So we talk about this in atmospheric studies, environmental concerns, pollutants, whether it be air, water, whatnot. Back to the more basic sense, you guys sitting in front of me right now studying geology, mineral is composed of one or more elements. All right, in lab very soon we're going to get started talking about minerals, and you guys, not for testing purposes, we've got something slightly less difficult for testing purposes, but you guys are going to be looking at the formulas in order to put them into their groups. And you're going to see that some minerals are composed of just a single element, not a whole lot, and others are composed of multiple elements. You folks in earth science will do this as well to some degree, but not until later in the semester. Anyhow, going back to minerals being formed of elements, guess what? Rocks are made of minerals. And the earth is made of rocks and minerals and elements and ... So I mentioned to you earlier just in passing that I like to sort of back up and take a broader view of things, okay, sort of a holistic approach, if you would. And when the semester lets me, we back up really, really far. I think it helps you guys to understand not just where conversationally we are in geology, but as you go, forward in life, if you understand kind of how we got to where we are. So at the very least, we'll talk about how the earth came together, And like I said, depending on my mood and your guys' mood, I gauge things a little bit based on perceived interest levels, if we go all the way back to Big Bang or not. So we'll see where that goes. All right, and that is